In section 6.4, part 3, we take the idea of permutations to another level and talk about permutations involving like objects. So the permutations in the previous examples have all involved sets of distinct objects that kept saying distinguishable. You can't tell the difference between one person and another, one horse and another. I'm sorry, you can tell the difference between horses or between people. So in many situations, we need the permutation of a set of objects in which not all of the objects are distinct. Now I'm going to write the formula on the board, and it won't make any sense until we go do an example. So have a minute, patience with us. So permutations involving like objects. So permutations of like objects, not repeated objects, but like objects. And the formula comes out to be n factorial divided by r sub 1 factorial times r sub 2 factorial times dot, 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 all the way up to r sub k factorial. So it's an ugly looking formula, but it's a lot easier to use than it is to memorize it. So it simply says that if a set contains n elements of which r1 are one kind, r2 are of another kind, and so forth on through rk, then the number of different arrangements is given by this formula. So what do we mean by like objects? So we're going to take a look at example 7. Example 7 says, find the number of rearrangements of the letters in the word parallel. P-A-R-A-L-L-E-L. Parallel. Okay, so the first thing we're going to do is figure out how many letters we have to be arranging each time. So if I count up the letters, I've got 1, 2, 3, 4, 5, 6, 7, 8. So we're going to start off with 8 factorial. That's the top number. That's the number of objects we have total. Now the bottom number is going to account for all my letters. Well, there's only one P, so that's not very exciting, but there would be a 1 factorial sitting there, and that would be for the letter P. Now I'm going to move on to the next letter, which is an A, and we'll notice that we have 2 A's. So I now need 2 factorial because they are like. In other words, when I go to rearrange these and I write P-A-A, I don't care if this A is this A or this A is this A. So they're like objects. I can arrange them in any order. We're decreasing the possibilities because of that. So we're going to multiply this by 2 factorial, and that takes into account the letter A. Our next letter is an R, so that's a 1 factorial for the R. But we do have lots of L's, so 1, 2, 3 L's. So we have a 3 factorial, and that accounts for the 3 L's. Finally, there's an E, that's a 1 factorial for the E. Okay, I really don't need the 1 factorial, so we're going to abbreviate this down or simplify that, I'm sorry, to just the 2 factorial multiplied by the 3 factorial. And then you can go to your calculator. Make sure you put the denominator in a set of parentheses, otherwise you'll get the wrong answer. So 8 factorial divided by 2 factorial divided by 3 factorial, just to give you some in-between steps, that's 40,320 all over 12. 3 factorial is 3 times 2, that's 6 times 2 is 12. When you divide that out, there are 3,360 ways to rearrange the letters in the word parallel, to use all 8 letters and rearrange them. Now, whether or not they spell word, that's not what we're doing. We're just looking at the number of ways to rearrange them. So another example of permutations of like objects would be example 8. So example 8 says, how many different ship signals can be made by hoisting 2 blue flags, 4 white flags, and then finally 3 yellow flags? In other words, you're going to put all of the flags, and how many do we have altogether? 9 flags, so 2 plus 4 plus 3, so we've got 9 flags total. You're going to put all 9 flags up on the mast. How many different ways can you arrange those 9 flags? Well, the blue flags don't matter whether it's the first blue or the second blue. You're going to be using those blues. That's why they're considered to be permutations of like objects. So our answer is going to be that 9 factorial for the total number of flags, divided by 2 factorial for the blue, multiplied by 4 factorial for the white, multiplied by 3 factorial of the yellow. And what we're recognizing is that because they're like objects, the total number of possibilities is going to be less, because running up blue 1 and then blue 2 or blue 2 then blue 1 doesn't matter. So again, put the denominator in a set of parentheses, and I have that that's 362,880 being divided by 288, which comes out to be a total of 1,260 ways to put those 9 flags up the flagpole or mast.